Welcome to another edition of RCE. Again, this is Brock Palen. I have again with me Jeff Squyres from Cisco Systems and OpenMPI. Jeff, thanks a lot for your time.
Hey, Brock, how's it going?
All right. You can always find all of our old shows at rce-cast.com. Also, you can subscribe from there. There's an RSS feed, link to iTunes. Use your favorite podcatcher to check anything out you want to look at. Today, though, we have a guest from an organization that has been on here before, and he's going to be talking about some Python stuff. So, Stan, why don't you take a moment to introduce yourself?
Hi, I'm Stanley Siebert. I'm a software developer at Continuum Analytics, and I work on the Numba team. Although my previous career, I was a particle physicist working on neutrino and dark matter experiments, but I was also a big Python and GPU computing advocate, which sort of led me back into software engineering.
So you mentioned that we're talking about Numba. Can you give us a quick overview of what is Numba? Yeah,
so Numba is basically a Python compiler. It's designed to compile Python functions, so you may be familiar with other Python projects that take your entire program and try and optimize them in some way. Numba is a little more specific and will let you take a particular function and say, I'd like this function to go faster because I'm only going to use it with certain data types. I'm only going to pass in arrays of floats or that sort of thing. And then what Numba can do is analyze the function, take this extra information you've given it, and generate machine code that does just the thing you want very quickly. At a higher level, Numba is really, its goal is to try and help you, if you're in your Python programming, if you get to a point where your Python's not fast enough and you need some kind of sort of smooth way to speed it up, we want you to be able to keep working in Python and not have to switch languages out to C++ or Fortran or do other, switch Python interpreters entirely. We're trying to give you a smooth ramp from your initial prototype to a faster version of your program.
So how did the Numba project get started?
So actually, Numba was originally started by Travis Oliphant, who you've had on the show previously. One of the main founders of NumPy, was actually trying to find a way to write specialized functions for NumPy. He was trying to do some element-wise calculations, and he wanted to generate functions that were as fast as a compiled language. And so he actually went and discovered that there was some old Python bindings to llvm, which is a fairly standard compiler toolkit. He resurrected those llvm bindings and then started building Numba, which was sort of designed for a very narrow thing, but then he started hiring more people to help him expand it into a general Python compiler framework.
Okay, so do you compile, are you doing code translation, you're turning it into C and then sending it to a normal compiler, or what exactly is going on here?
So what's actually going on is it takes it looks at the Python, so it's a runtime compiler. So it's not like GCC or something where you run it to compile your program. When your program starts up, at either the point where you define the function, or you could decide manually later to take the Python bytecode, and then it translates it into the llvm intermediate representation, the llvm IR, and that is fed into llvm, which is another project that does all of the generation of machine code and everything. So we never pass through C or anything else. llvm kind of looks like a high-level assembly language. So in a sense, Numba is acting as a front end, and llvm is acting as the back end of a compiler tool chain that you can run in the middle of your program.
So llvm is probably best known as part of Clang. It's not normally known as a runtime compiler. So, how slow or fast is this, the first time you hit something?
It's not too bad. I mean, again, because Numba lets you target specific functions, you don't have to compile a whole lot of code often to make your program run faster. You can identify a couple of critical functions, target those directly, and then you can be generating this code in less than a second for a reasonable sized function. And then that overhead's only really when you start up. And then for the rest of your program, of course, you are just directly running the function you already compiled.
All right, so how did you pick llvm? Because like Brock said, this is not what it's typically used for Although LLVM has been used for more and more interesting things over time, like you said, mostly known for Clang, but has been used in some other offshoot projects. I mean, do you work with some language people who kind of suggested that, or where did this all come from?
LLVM, I think, became a really easy choice early on because it's a very modular system. It's really a toolkit for building compilers, and that's what we wanted to do. And we didn't want to have to figure out all of the optimization passes in the whole backend. I mean, in some ways, LLVM preceded Clang, and so LLVM was being used for a lot of academic compiler research, but has now become, with a lot of commercial support, is being used for Clang, obviously. A lot of other companies have adopted it. NVIDIA's compiler toolchain for their GPUs now uses LLVM, and AMD is using it, and a lot of other places have picked it up. And so actually one of the advantages to Numba using LLVM is now we get access to all of those other architectures. Numba can compile code for the GPU, which is, I think, one of a huge point about Numba that separates it from similar projects is we can target both the CPU and the GPU thanks to using LLVM.
Now, actually, let's dive down on that point there, because that's an interesting little bit there. And I am fairly ignorant of GPU stuff, so forgive me if I ask something really silly. But targeting the GPU is one thing, but then you also have to add additional stuff to move the memory back and forth and handle the registration and things like that. So do you have additional code in Numba that handles that kind of logic when your target is a GPU?
Yeah, so when we add a new target to Numba, we include both some driver level stuff that lets you, manage the device, open up a connection, move data to it. In some cases, Numba will move the data for you. You often, as a first pass, don't have to worry about that yourself. We'll copy it over and then copy it back. Sometimes you want to control when those copies happen, and so you'll use our the device API basically to say, okay, now I want you to copy it, and then I'm going to wait to bring it back until I'm done with my whole calculation. But that's sort of a little bit of infrastructure around the core LLVM piece, which is shared quite a bit between the CPU and GPU targets. A lot of that is similar code thanks to the LLVM abstractions.
So what if I wanted to, instead of using it as a just-in-time compiler, actually kind of, say I know I'm going to run something many, many times, can I kind of save that compiled state?
Yeah, so we have a tool. It's I would say it's not quite ready for prime time, but we have been working on called PyCC, which is job is to do exactly what you're describing, and it's certainly on our roadmap to flesh that out so that you can take a file of Python code and say, I want to compile this to a compiled module that I can load it into Python later and just call and not have the compiler overhead. But right now, pretty much most of the use cases for Numba have to be runtime compilation, which, as I said, for a lot of projects you just don't notice. There's enough other stuff going on. You're not compiling your whole program. But certainly we want to support libraries of standard functions that people write and want to just reuse over and over.
Now, you said earlier that it took the Python bytecode. Which is it, or does it do both? Can you take both, just scripts and parse the ASCII, or maybe the Python interpreter does that for you, or do you only read Python bytecode?
So we read the bytecode because at runtime, once you've read the ASCII function basically in, the Python interpreter converts it to bytecode immediately. And so at runtime, the thing we have access to is that bytecode. We do have, people have done code generation where you generate a Python string and then you ask Python to convert that to some bytecode, and then you can hand that off to Numba. But we don't want to re-implement a Python parser, but that's already built into the interpreter for us, so we don't have to do that. Gotcha.
Now, when again, here's some ignorance of Python itself. When Python generates the bytecode, regardless of whether it's in the separate compile step or at runtime, does it do anything like what LLVM does itself, or is it pretty much just a straight translation?
It's a pretty simple translation. The bytecode is all of the different constructs you have in the function get turned into a sequence of bytecodes. The bytecode is really just there as an interpreter convenience, that it's easier to write a fast interpreter that deals with bytecode as opposed to a more high-level construct. And since that bytecode is what's really sitting in memory when